Have you tried ChatGPT yet? Or any of the other commercially available so-called AI products? They're not really artificial intelligence. I mean, there's no reasoning going on under the hood. What ChatGPT and others are language learning models, meaning they take in information and they quickly find patterns. As a tool, alongside other things, I suppose ChatGPT has its uses. Here's an example. Say you put an LLM on your EDR. Thousands of security events go by every day, and over time the LLM begins to learn what is normal background network traffic, isolating the few events that are anomalous. Those are the ones that the analyst should really focus on. This is a simple signal-to-noise example, because it saves time and it relieves the tedium that junior-level analysts have chasing down false positives. It can also identify the tactics and techniques of a bad actor quickly, so you can mitigate that. Another example would be to identify an attack approach for a pen tester. Say you need to find a particular operation like XOR on a table lookup, and finding that leads you to discover some secret data that, well, is not secured. You'd want to find that, but doing so, it's kind of tedious. So here's where something like ChatGPT would be advantageous to a researcher for preventative work, or to a bad actor for something more malicious. Okay, maybe such attacks seem far off. Then again, given the way ChatGPT has taken off, maybe it's not. This is the story of how one researcher at Black Hat Europe got ChatGPT-4 to perform correlation power attacks on real hardware. It shows how ChatGPT can speed the analysis, and therefore why we should be securing our embedded circuits today. I'm Robert Famosi. This is Error Code.
My name is Witold Waligora, and I'm the founder and CEO of CloudVA, which provides remote access to hardware and software for side-channel analysis.
I spoke to Witold shortly after his Black Hat Europe presentation, how we taught ChatGPT-4 to break mbedTLS AES with side-channel attacks. He seemed very surprised that I would even be interested in side-channel attacks.
You know, hardware people are sometimes interested, but it's very rare for media to get interested.
If you go back to episode 8, I did talk with Ang Kui of Red Balloon about side-channel attacks against Siemens S7 1500s. So, if all this is new to you, I did ask Witold for his definition of what a side-channel attack is.
So basically, when you compute something on a physical machine, this is physics, you use energy, you use time, use other resources, and there are also emissions that come with it. Physical emissions like radio, heat, audio, and of course power also can be detected. So these are side-channel. Analysis of these effects is side-channel analysis.
So side-channel is an area I think more people need to know about. So that's why I'm doing a podcast, again, about this topic.
As I said in my presentation, I think side channels are underappreciated and they are actually easier than people think. There is some, math involved and some, high barrier of entry. But once you do that, it's portable. They are very portable. So you can attack many chips and many software implementations with the same exact attack, for example. It covers a very wide area of a very wide market.
So essentially, you're observing something that is happening and you're inferring what is happening.
Yes. So we're observing something that happens on the physical machine during the computation.
And somehow all this gets you ones and zeros. I know, it's a very simplistic explanation, but the point is it can get you some data.
Yes. So basically, in this, to get a little bit technical, in the CMOS process, which is 99.9% of today's chips, what leaks is, so power is consumed when a transistor changes state from 0 to 1, when it switches. So these switches can, so basically by observing the power, we can observe transistor switching.
CMOS stands for Complementary Metal Oxide Semiconductor, which is a type of metal oxide semiconductor field effect transistor, or MOSFET. All right, a lot of acronyms, not a lot of meaning. Simply put, CMOS technology is used for constructing integrated circuit chips, and it uses positive and negative voltage to reflect ones and zeros. So if you can listen in on that, you can steal the data from that transistor.
Yes, of course, the problem being there are millions or billions of transistors, so you need there is a lot of noise also, so you need a lot of samples, a lot of measurements to kill the noise and to extract the information that you're seeking from, the other 99 million transistors that you're not interested about.
So that raises a question. Can you do this out in the field, or does it have to be done in a laboratory?
Of course, in lab, it's much easier because you can access the power rail and the signal is much less noisy, but you can also do that in the field. You can do that remotely with a radio antenna, for example, from a small distance to the chip also. So you have also non-intrusive access. That's also possible. Of course, this requires much more samples because the noise is higher, but it's also possible.
So Witold was looking at something called mbedTLS. What is that, and how is it being used?
So we were looking at mbedTLS, which is a library for encryption, so bare metal encryption on many of the embedded chips, so STM32 whatever or ASP32 whatever. These use quite frequently the mbedTLS library. This library, I think, is more than half of the market today. Collectively, there are like 3 libraries that only use. So it's OpenSSL, of course. There's mbedTLS, and there's some tiny IES implementations. This is a small reference like implementation of encryption. But these 3 collectively cover, I think, more than 90% of the market today.
And mbedTLS is more likely to be used with IoT devices.
Yes, it's far more likely to be used with IoT devices, especially the ones that don't have an operating system. So for bare metal devices.
And when we talk about operating systems, we're inclusive of real-time operating systems, right?
Yes. RTOS was included. So if you have RTOS, you can use OpenSSL. But if you don't have RTOS, OpenSSL, it's still possible to use OpenSSL, but it's very difficult. So you would go to mbedTLS.
So you're looking at the embedded communications between devices in the field and their networks.
Yeah. So different components of SSL. At the presentation, we were attacking Advanced Encryption Standard specifically, but we also have attacks on asymmetrics, RSA or elliptic curve cryptography. We also have attacks against that. We also have attacks on post-quantum crypto. That's not even a standard yet, but there are also side channels against that already.
Given all the different encryption standards out there, why did he stick with AES encryption for this presentation?
It's something that most people are familiar with, that it's most popular, most understood, and also it's the easier to show live because it requires the least amount of traces and fails basically never these days.
Okay, so now we're going to talk about language learning models. And for this presentation, Witold used ChatGPT to basically perform a side-channel analysis. A lot of that came down to coming up with the prompts and the filters that were necessary.
The idea behind this work was that for side-channel analysis, basically you need to know 3 things about code. So you need to find a particular operation, like XOR or table lookup, that's performed on secret data combined with user input, so with data that is non-static, that comes from outside of the chip. So controlled by an attacker possibly, or at least data that varies enough that we can calculate statistics on. And these are 3 questions that GPT is quite good at answering. We found separately. Combining these three is a bit tricky. With prompt engineering, it's possible, but it's harder to answer all three simultaneously than separately. But it's possible, and we did that, and this was the base of this attack. Basically, GPT detects the vulnerable spots for power analysis in a particular piece of code. In case of Advanced Encryption Standard, it already knows the algorithm, so it's easier for that also. But you can also attack arbitrary code. We've done this also. You can paste arbitrary code and ask it to analyze this particular piece, or tell it to construct a side-channel attack against a particular variable, and it will also do that, basically by the same analysis.
So for somebody who hasn't yet used the AIs or language learning models that are available, I wondered if we could talk a little bit more about the prompt engineering that goes into it and how the prompts are so important.
Yes. So the basic operation of LLMs, of GPT and other LLMs, is that they only predict the next most probable token. So you have to guide it to you have to guide it with prompt engineering to the solution that you want it to generate. You have to be very specific, and so basically it has a ton of knowledge, but it can't really apply it by itself. You have to guide it.
I should probably explain that Witold is not feeding live data into ChatGPT.
No, what we've done is we provide endpoints. We provide functions to the GPT that the GPT model can call and collect data and analyze the data. There is too much data to feed directly into the GPT model to process. It would be possible on a smaller scale, but it's also not a good idea. GPT is not very good at math by itself. Like I said, it predicts the most probable token, but it's not calculating. Like, it's not doing math correctly. It's just guessing pretty much, and sometimes it guesses incorrectly. So basically, we collect data. We hold the data outside of GPT, but GPT generates the function calls and the queries and the patterns to detect and analyze with the data to operate on this data.
Bottom line, language learning models, they save you time.
Yes, and that's a lot of time. So basically, the way we're working with our plugin, with our GPT right now is I can ask it to evaluate 15 leakage models, and it will tell me which one is the best. So I would tell it, here's 15 leakage models, evaluate them for me, and I go for coffee. It can also do bisection. So you can ask it to find out how many traces, so how resistant is a particular implementation to this attack, and it will do bisection, so binary search on the number of traces needed to break the key on its own. We don't tell it what to do, really. It figures this on itself.
And language learning models, it's like having an assistant.
It is an assistant. But it's a clever assistant. It analyzes the code, so it generates the patterns for the attack. It analyzes the code. It extracts the leakage model. One thing we also tried to do, this actually failed, but for a reason that's I'll get to that later, is replicating side-channel publications automatically with GPT. So basically telling GPT, here's a paper, extract leakage model from it and apply it to our environment, and run analysis with it. And this one, where it breaks, is actually loading the PDF with scientific notation intact. So once you provide it with scientific notation that's actually correct, most of the time it will generate correct code and it will launch a correct attack. Where it breaks is actually loading the document. So that's the weak point in this model currently.
So by asking a language learning model to generate, say, malicious code or an attack, does that get into licensing problems? Are there issues when it comes back and says, hey, I can't really do that for you?
There are filters that you hit when you do that. These are easily bypassed by some prompt engineering. So, for example, we had to rename the attack that we did on Black Hat was correlation tower attack. but we had to rename it to analysis because model wouldn't do it otherwise. Other than that, yes, there are terms of service issues, and basically for our use case, this is okay because we are not doing this live on someone else's code. It's a lab assistant, and you have to have the device connected to our environment anyway, so you can't really use it outside of our lab. So you don't have any issues of this spreading out in the wild.
So there are a lot of different language learning models out there. I just wanted to clarify, for this presentation at Black Hat Europe, this was ChatGPT and not the one that you can get on the internet.
The presentation on Black Hat was with ChatGPT-4 with plugins. We built a plugin for ChatGPT, and the plugin is available in the plugin store for if you have access to the developers, the dev store. It's not publicly accessible at the moment, but it's a beta access. But of course, we also use offline non-ChatGPT version locally. This is better. It's faster and it has less filters, and it's also a newer model. The ChatGPT is based on I think June model, if I remember correctly these days. But the latest model is better.
So how is a language learning model actually used in a side-channel attack analysis?
Yeah, so basically our goal is to lower the cost of side-channel analysis at least 10x. So currently what you would do, you would have to go to the big boys, we call them. There are 4 certification labs that do side-channel analysis. These are Brightside, Rescuer, T-Systems, and the 4th one I don't actually remember the name of, but these are crazy expensive. They do full certification, of course, which we don't do, but for IoT security, you don't need that kind of security, and you cannot justify that cost. But still doing some side channels would be nice, because otherwise, a teenager with an oscilloscope can break your device. So we aim at this lower end of the market, and our idea is that once you have a hardware prototype, you would ship this to us. We would connect it to our lab, and we give you a VM with all the software and hardware connected to your device, and then you can iterate software with a standard GitHub CI/CD pipeline with side channels. So we can run side channels like a regression test, and you also have GPT assistants to do that. And you can hire any experts on the planet, or us, of course, also to do this analysis for you.
Maybe a better question is, who would actually be asking him to do this type of analysis, and why?
We're working with small vendors, currently beta access to this framework and to the lab to do these small scale side channels that we call them. It's not a full certification, not that we couldn't do it. We actually had we were involved in a certified product before, but we're aiming at the lower end of this market because we think that basically there is no side channel protection on these devices at all. They are breakable within seconds. And the attack that I've shown is 12 seconds. Exactly. And it's not the best attack. And it's not the best attack that we have. The one that's the easiest to present.
So given that we know that these attacks are possible with devices out in the field, what sort of mitigations exist?
There are some easy protections you could do even without changing the core. So we have, for example, we introduce some noise through PLL, a loop with randomized frequency, for example, and this increases the attack complexity. So from seconds to hours, and by the time you have to set, 3 hours on someone's parking lot collecting data with an antenna, it's not a good idea. So basically, there are some small tricks that you can do to increase noise dramatically during the critical periods of the computation. And also there are some small tricks to the implementation that you can do to increase resistance.
So one of the problems with doing this analysis on a device is that there are a lot of transistors And identifying which one you want to introduce the noise to, well, that adds to the complexity.
Either noise, there are basically two ways to do that. First thing is the easiest, so introduce noise, outside noise, inside noise. So outside noise you could turn on if you have a board, and you could turn on some other device on the same PCB that you're not currently using, but you can turn it on just to increase power draw and increase noise, by the way. But also there are things that you could do to hide your computation. So for example, if you slip one transistor, you could flip another transistor the other way, and these kind of cancel out. So basically you can calculate a negative, we call it a power negative. You could apply a power negative calculations in parallel to your encryption, and this also hides the calculations quite well.
So all of these devices are still capable of being compromised. It's just you're increasing the barrier between the attacker and yourself.
This is for side channels. This is always true. There is no way to protect against side channels in the absolute sense. It's always a matter of how expensive, of how good an oscilloscope I can have, and how many traces I need. There is no way to protect against it, and it will always be breakable. Against it, no chip is safe against side channels. It's only a matter of how many traces and how much computation and how good an oscilloscope I have. That's the only three variables.
So there are a number of different physical things that you could tap into for side channel analysis. Is there one that Witold prefers?
Power is easiest, I think. Technically speaking, active attacks, so fault injection, it has the best success rate, but it's also not safe. Like, you can literally damage the chip that way. It's not a high chance of damage, but there is a chance of damage. So these are things that you would like to avoid in a regression testing setting. If you run the same attack like 1,000,000 times, it's probable that one of them will damage a chip. So passive attacks, we prefer passive attacks for what we do. And within those, we prefer power analysis, because this gives us, so for example, you can do timing analysis also with power. So you can detect features within a power trace, and you can observe how these features appear in time. And this gives you a timing attack, a much more powerful timing attack than just observing how long the computation takes start to end. So power is the starting point from everything, for pretty much everything.
Witold mentioned passive, and I'm assuming the other is destructive, where you would physically take something apart.
I guess multiple dimensions to this. You can do passive attacks that are intrusive. So basically, you would have to cut a path on the PCB to access the power rail. That would be an intrusive attack. Or you could also take off the protective coating of the chip and access the chip itself. That's also an intrusive attack, but it's still a passive attack, because you're not perturbing the operation of the chip, you're just observing it. By active attacks, I mean shooting lasers into the chip, or shooting electromagnetic pulses into the chip, or altering its power. So overclocking, underclocking, overvolting, undervolting, these are active attacks.
There are many different ways to do side channel attacks. Some of them are still theoretical. I asked Witold if there's something out there that's like really hard to do, but gosh, it would be really cool if we did it.
It's not a recent paper, but I've seen a paper that takes a screenshot of a monitor by listening to the noise of the capacitors.
Okay, this is cool. It's where you'd be able to reconstruct what was on a monitor screen simply by listening to the noise produced by the chips. This would be like an audio side channel attack, except the result would be an image.
So audio side channel against a monitor. This sounds like science fiction even to me. It was a published paper. We would like to replicate this at some point, but it's quite a lot of effort and a little bit out of our way at the moment. But this sounds like science fiction to me. And it was a published paper. So pretty sure it was working at some point. But I wonder what the lab setup for it, for that was, because it's one thing to do that live, like in a couple of seconds or minutes, and it's another thing if you need to listen for like 3 days straight to the same image to do that, right? So I wonder what was what's the amount of data that you actually need to collect to do that. It wasn't strictly specified in the paper, but this is one thing that comes to mind when I think of science fiction like side channels.
This sounds like Tempest. Tempest is an NSA program that can spy on information systems through leaking emanations, including the unintentional radio or electrical signals, sounds, vibrations. The idea is that you can get sound vibrations off of an old manual typewriter or even window panes and reconstruct that data.
But I think this is harder for the one that I mentioned, because especially the microphones that you have around, whether it's your phone or your headset, they are not high quality microphones. So the amount of noise they pick up is massive. So to kill that noise, you need a crazy amount of data, and capacitors are not noisy enough. That it's a high pitched noise in a specific frequency, I guess, but still, it would, in my mind, it's crazy the amount of data that you would have to do to kill the noise for an average microphone, for example.
So does Witold do audio side-channel attacks?
We don't do audio. It's not in the frequency range that we're interested in. So if you were attacking like a kilohertz chip, it would be feasible to do audio attacks. But even in our IoT, everything is in tens or even 200 megahertz range these days. So it's way beyond any range that's pickable by a microphone these days.
So Witold gave his talk at Black Hat Europe, and I'm wondering, were there any interesting questions that came after the talk?
Yeah, a little bit, but most of them were about AI, not side channels in particular. So most people were interested in GPT and how it performs against on code analysis and whether it can analyze or generate exploits. Answer to that question is it's both better than you think and worse than you think. So it fails in ways that you wouldn't expect, and it also succeeds in ways you wouldn't expect. So it's surprising on both ends. For side channels, yes, we had some questions about extracting, so attacking hard drives, for example, or crypto wallets. That's a very good target for active side channels, so fault injection, for example.
Okay, earlier Witold alluded to a failure, and I just wondered what that was.
Basically, what we think is that the model itself is very good quality. So model itself works. What breaks quite often is the input-output of the model. So for example, like I said, with the PDF, with the scientific papers, what fails is not the intelligent processing of the scientific notation, but just loading the scientific notation in the form that's actually correct. That we see very often. So, for example, I can have GPT analyze a screenshot of my. I have an assistant that I written like yesterday that analyzes a post on Twitter, and it can write the code from a screenshot. And when it breaks, it's actually not processing the code or transforming the code, but just loading the image. Like processing the image is the hard part, not processing the text data. So that's something I think people are not aware of, that models, the bottlenecks are not within the models, strictly speaking, but with the integrations of the models with the rest of the world. So the hard part is loading the data, not processing the data.
I'd like to thank Witold for coming on and talking about his use of ChatGPT to set up side-channel attacks on IoT devices. Not for the malicious reasons, but for the preventative ones. It's good to see device manufacturers stepping up. And while I'm skeptical about language learning models in general, I do see how they can save time in finding needles within the haystacks. Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Join us on Discord. Search for Error Code Podcast to join the server, or go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. Hey, I've got some great episodes coming up, including using EDRs to attack enterprises. And more on IoT and OT, of course. Subscribe today. I don't want you to miss out.